AGI, right? And then efforts to speed it up. Then we'll have a couple minutes for lunch, and then in the afternoon, we will hear more about some things people are doing with Meta right now in terms of learning and reasoning and so forth, which is relatively small scale and prototyping, but still quite interesting and showing some of the future directions we'll take once we've scaled up the interpreter. And I think right after lunch, I'm giving the first talk, which is about a cognitive architecture I now call primates. It was called Cog Prime in earlier publications. That seemed like an ugly name. So we decided to rename it after the all-knowing, all-powerful force of good from the Transformer cartoons. Because Transformers must, in some form, take over. So, yeah, after lunch, I'll talk a bit about the Primus cognitive architecture, which is like how do we use all this cool infrastructure we'll discuss in the morning to actually build a thinking machine. And then we'll hear about some practical stuff being done in meta language now. So for now, I want to start with the hands-on meta language stuff, which is going to be folks video chatting in from St. Petersburg. Then after lunch, I will launch into the in-depth discussion of how to build a human-like cognitive architecture using all this super cool infrastructure. So is Alexey next? All right, so our next speaker is Alexey Potapov, who's Dr. Alexey Potapov, whose work I was following for some years before we began working together. I think he's been the leading AGI researcher in Russia for quite some time, and was an academic at the ITMO University in St. Petersburg. And I was really psyched starting 2018 or so to recruit Alexey to join my own AGI efforts, and it's been now a joint AGI effort, sort of working together to pursue our visions in a synergetic way. Because I said for a long time there were more AGI designs and AGI researchers, right? Like it's very hard to get two AGI researchers to work together. It's very hard even to get the two halves of my brain to work together sometimes, right? So getting a number of different AGI researchers who've been thinking about AGI a long time and have their own sort of singular idea how to do it. Getting a bunch of different AGI researchers to collaborate on one system is often a large challenge. And so I think Alexey and I have managed to figure that out, and our approaches are not identical, but are aligned enough that we've been able to work on building the same system and cognitive architecture. And one of the outgrowths of this collaboration is the meta language, which sounds better with a Russian accent. So let's hear from Alexey. A big A.
Hello, Alexey.
Hi. Well, the issue is that we have not been receiving any video or audio from your side for the last 50 minutes, so we are not sure what's going on. Could you please turn on your video as well, maybe?
Do you hear that? They're not getting video?
Yeah, so the guys messed up something right here, so he just messed up links and showed private stream instead of public. I showed, like I told him.
Yeah.
So it was like...
Is it working now?
It's working now, because he just, you know...
I can hear
He still says he doesn't see it.
It should be working.
Yeah, now we can. We haven't been able to hear since 9 o'clock.
Right now it should be working. It should be fine. So he told me that he just put private setting yesterday while testing, and he didn't remove it. So the whole stream was private. So.
Started with what?
I'm sorry, Frank gave his intro and he was handing off to you for your presentation.
I believe it's not my presentation, but Vitaly Bogdanov should start.
Okay, yeah. Yeah, first, could you hear me now?
Yes, please go ahead.
Is it okay? You sound
Please
from
go
me.
ahead, Vitaly.
Okay. Okay, thank you. Yeah, we discussed with Alexey that I will start with some introduction to Meta fundamentals and some hands-on experience with Meta. Yeah, we share the screen. Okay. Yeah, first of all, I would like to share, can you see the slide?
Are you able to stream from here?
Sorry, I can't hear anything.
Yes, we can hear you.
I can see.
Okay, thanks, Greg. So I would like to share some hands-on experience with Meta and explain Meta programming basics and show some examples and probably make some review of the standard library, Meta standard library, which is implemented in Hyperon experimental Meta prototype. And yeah, this is linked to the examples repository I prepared before the workshop. I would not, I will not take these examples literally, but this link contains a small instruction how to set up Meta if you don't have it right now on your host. There are 3 different ways. You can probably link can be shared in some chat or something. I will try to keep it on screen as long as possible, but right now I will just click on it. Okay, and yeah, there are 3 ways to run Meta interpreter. Basically, most reliable and the most simple way is running it using Docker. You can just clone a repository with examples, change directory to this repository, and run Docker container with mounting this folder inside it. Inside container, you will have Meta repo, which is repo implemented in Rust, which has many different pieces like code highlighting, history keeping, and some. It's very useful for playing with meta code and starting with short examples. And you can also use it as a file runner. You can just run Meta repo with file and execute it fully. Other ways to run it is using Python PyPI package. It's not actually, it doesn't contain a repo implementation because it contains only Python implementation of the Meta interpreter. But it's very convenient to experiment with Python code and Python integration with Meta because it's run from Python interpreter. It can provide more stable and reliable integration with Python. And certain hardware is built from source. Actually, to build repo open source, you need only a stable Rust toolchain and just call Hyperon experimental repository and install the executable net repos, and you have repo installed on your PC. But actually building the full system is more complex. There is a long build instruction. I wouldn't recommend it for this workshop because it's very time consuming. Probably can cause some issues in complex environments. So I personally will use Docker way for this demonstration, so I will just copy this and do it here. Okay, now I'm in Docker with mounted examples folder, and I can run the repo, which is net repo implementation. Okay, let me start from explaining what metaprogram is. Actually, metaprogram is an atom space, is a knowledge base, which contains both data and rules of its processing over functional codes, which can be executed by running net interpreter. Atom space is a storage for the atoms. Basically, in Hyperon experimental, there is a simple atom space implementation, which is basically just a collection of atoms. Atom space provides methods to query atoms and transform atoms or replace atoms inside atom space. So atoms are basic building blocks of the space, and they are units of information which is kept in space. Atoms have 4 different kinds. So the simplest atom is a symbol. For example, I can type some symbol here and press enter. It means that this symbol is added into the current context atom space of the net interpreter. Symbol is specified by its name, which is subsymbol right now, and 2 different symbols with the same names are considered equal. So if I type it again, it's the same symbol actually. I also can add another kind of atom, which is expression. It can be, you can think about it like about tuple, which contains other atoms, for example, symbol or another expression or more nested expressions, something like this. And after I press return, this expression is also added into the atom space. Third kind of atoms is a grounded atom. Grounded atom represents subsymbolic data which contained in atom space. It's, for example, numbers or strings. And also grounded atoms represent grounded procedures or functions, and they also represent grounded collections. So some binary data which can be queried and modified somehow. For example, space itself is also a grounded collection, so you can think about space as a grounded atom. So I have added some atoms into the atom space, and how I can check what atom space contains. To check the contents of the atom space, I need to execute grounded procedure get atoms. The execution is done inside REPL or program by prefixing atom by the exclamation mark. So
Hey, Vitaly, could you increase
here
your font size?
I write the expression get atoms and so. It is a function call. The get atoms is a grounded symbol, grounded atom, which
Vitaly?
represents. Sorry. Yeah.
Is it possible for you
It's
to,
probably to.
is it possible for you to increase your font size like that?
Okay. Sorry, I forgot about it. Is it readable now?
That is true.
Okay.
So now,
Is it
that is a bigger size, but it's not quite aligned. Like we can't, or is it? No.
Minus 1 or 2 sides.
I guess it is. That's good, actually. Yeah, that's good.
Okay.
Yeah.
okay?
Yeah, thanks a lot.
Okay. So this expression means that I'm going to call grounded function get atoms, which has a single argument and it should be atom space. Ampersand self is a atom which represents the current atom space, which interpreter is working with. So now we see atoms we added just recently, some symbol, some expression, and a couple of grounded atoms. We also can add some information into the atom space and try to query it using match grounded function, which takes space as a first argument, pattern which we are looking for as a second argument, and some atom which will be returned back if pattern is matched, which can contain variables on the pattern. The fourth type of the atoms, which I didn't mention yet, is a variable. In a meta program, variables always prefixed by $sign, so we can execute it and see what happens. Match finds this pattern with the atom space. It matches this atom, and variable what receives the cat value, and cat value is returned. Really trivial, but it is main operation which is executed by the interpreter while evaluation, while interpreter is evaluating the atoms or data programs in the meta programs. Okay. So, how interpreter actually works? When expression is evaluated, the first atom in the expression is considered to be a function, and it can be a grounded procedure or a pure meta function. Right now, we till this moment we saw only grounded function code, but we also can add custom functions into our atom space and execute them. In order to add some function, we need to add equality expression. For example, some trivial function, but named hello, which prints some message on the screen. by adding this expression, I also defined function hello, which can be executed by the interpreter and actually does what is supposed to do. It prints hello world message. Actually, the actual evaluation of this function is done by querying atom space using the following query. For example, we can do this manually using which. And if you do this, it also prints hello world. Facts to create printing, we can do the following. So we can see that match just founded the body of the function in the atom space and returned it. And as interpreter doesn't stop on the single step of evaluation, it evaluates the body further and it executes printf function, and finally this function shows a hello string. So basically the interpreter doesn't do anything else, so it just gets the function call, forms the equality expression query, finds the value of the function, and evaluates it further. That's all. Sometimes when expression has a grounded function as the first position, interpreter doesn't form the query, but just calls the grounded function with corresponding arguments. Let's write some small trivial function with arguments. For example, we can write function which has which increments task value using PR-prefix notation. For example, here, and this notation that corresponds to the list number, and we can execute it. Okay, you see that it returns the next number after that. So also can increment this number further, and this trivial function I wrote just to demonstrate that function definition can have also some patterns, and when interpreter matches the function call, it matches the patterns, fills the variables by values, and returns body with values instead of variables. Okay, we can also write something more less trivial. For example, adding two piano numbers. Now I have two different equality expressions to encode the same function. It is similar to pattern matching in other functional languages, but there is a difference. So it can this function is recursive, and so if we code on two piano numbers, we will get the result. So it is a sum of, so it's less trivial. It is a sum of two numbers. We also can use other function call as an argument of the function. For example, the same result can be received by incrementing z. And it demonstrates actually the one of important thing, that evaluation of the meta function call is done by evaluating arguments first. Usually it's done by evaluating arguments first. So here ink z and ink and z are evaluated before evaluating add. And it is the reason why add evaluation works smoothly and correctly. We can change the evaluation order by using types, but I will tell about it a bit later. Another thing which I would like to mention, that function can be partial actually, and can match only part of the possible arguments. For example, write some function. It's like x, but like if, but it is matched only with whole. Yes, but it is matched only if true is passed. So, if, for example, we are passing false, it doesn't match, and it demonstrates another specific of the interpreter. If interpreter cannot find the matching equality in the atom space, it just keeps expression untouched and not reduced. Thus, the evaluation of the expressions is going until they can be reduced further. If expression cannot be reduced, the evaluation stops and the result is returned. Let's write another trivial function to demonstrate that meta functions are non-deterministic. We can return few different results from the same function call. Here we are defining function bin, which can return 0 unit, and calling bin just returns both of them. You can combine this to get, for example, all pairs of zeros and ones. Basically, each call of the bin returns two results, and these two results and the pair of bin calls return the product of these results, which is a list of all the pairs. Okay, so next thing I would like to tell about is type system. But probably at the moment I need to stop and ask whether there are questions from what I already shown. Okay, if no questions here, I will continue. So all atoms in atom space are typed, and Usually these types are assigned by user. There are some situations when types are assigned automatically by the metaprogram parser. It is while when parser parses grounded atoms, it can which are presented in a standard library or another library which is imported into the program. Then grounded atoms usually are typed because imported module assigns types to provides the logic to assign types to the imported grounded atoms. We can find what type an atom have using get type one. For example, if you get type grounded atom 1, we will have type number. Or we can get type on some symbol. And we'll see that some symbol has a defined type. It is because we didn't assign type manually. To assign type, one can use colon operator, which is a reserved symbol inside meta interpreter. It is just a symbol, but you usually shouldn't reuse it in your programs because it is reserved for the type assignment purposes. So we can assign some symbol some type. This expression, which has 3 atoms inside, assigns type to some type, to symbol some symbol. And actually, if we now execute get type and some symbol, we will get some type instead of undefined. Undefined is a type which can be assigned to, which can be casted to any other type, but if symbol is, or other atom is typed, then typecasting should be some so either types should be equal or they should be matchable. For example, how we can use typing to improve experience with increment function we just wrote. Example, if I execute increment function on some rounded symbol which is not correct, I will anyway use see some result because inc function doesn't have type. We can check it. And type checking is not done for it, and argument can be anything. But if you want to restrict the arguments which function inputs, we can assign type to it. But first we need to assign types to that symbol and symbol we used. So that is just instance of the natural number type, and S is a function which gets a natural number and returns a natural number. Arrow is another reserved symbol which is used to assign function types for function symbols in Meta, and it is similar to Haskell notation, for example. So let us assign some type to function. It should take natural number and return natural number. Okay. Let's check it works correctly. It can work with that, can work with that, but if we execute it with some other type, it returns the type error. Okay. But if we will try to call in with some untyped expression, untyped SQL, it still will be executed. And it is actually it demonstrates that types in meta are gradual, and actually you can pass any value of undefined types into the function, and if function doesn't check manually which value is like need to be passed into it, it will still execute it. But if you want type checking work in your program correctly, you usually need to use only typed values. Okay. Meta also supports dependent types, and you can, for example, for sure it supports parameterizing types. For example, we can define some vector type, which is actually vector of some specific length. For example, the first argument of the vector type is type of the item. Next argument is the length of the vector, and as vector is type constructor, it returns type. For example, we can define empty vector as vector of zero length, and vector constructor which gets item of some type, gets tail, and returns new vector with incremented length. Let's check how it works. Get type on cons, here cons. Return vector of numbers with length 2. We also can use types to some kind of dependent types, some kind of type check. For example, we can define null function which gets a vector of non-zero length and returns vector with decremented length. If we write this function body and try to execute it, it returns new, but if you pass new, Okay, not a very good example actually. But you can see them. It is type error which prevents null from executing on an empty vector. Also, we can use types, as I said before, to control a variation order of the function. For example, let's try to write some function which returns first argument of the expression. Let's write it in this way. It just expects triple and returns the second argument, or the first argument of the triple. We can try it on some tuple and it works correctly, but if we will use a real example, for example, real function call, example function, which as sums two numbers, it will return incorrect result. It happens because interpreter evaluates argument of the first function first, and it sums 3 and 2, returns 5, and then tries to call the first arg. First arg expects triple, and it doesn't match with the function definition, so it's just not matched, and function call stays unreduced. But we can fix this issue with assigning proper type to the first arg. There are 5 special types which we call meta types, which basically are types of atoms. We can use them as usual types. For example, we can say that first arg expects expression, not some atom, but expression, and returns some atom. And if meta interpreter sees this type signature, it doesn't reduce the arguments before passing it to the function. So now first arg call works correctly. Expect expression and atoms are variable, rounded, and singular types, which can be meta types, which can be used also as a type of the argument. To get meta type, we can use get meta type function. Okay. There are also some special atoms which are reserved symbols, basically, which are can be used by functions or used internally by interpreter to modify the control flow. For example, empty atom can be used to return nothing. We can write function which returns empty, and this function just returns no result. Another embedded special symbol is not reducible. Which can be used, which can be returned from function to keep its call non-reducible, so non-reduced. So if you call such function, it just returns its call without any variation. For example, we can also have some argument, and the argument is also will be kept. And also one example of the reserved datum is error, which is used to return errors. If interpreter gets error from the function, it just returns it to the stack and finally stops interpretation of the program. Thus, error atoms can be used to send a message to the user about some internal error. Okay, the next topic I would like to discuss is the meta standard library. Some standard functions which are implemented inside the Hyperon experimental meta interpreter and which can be used in the programs. So, are there any questions so far about what I already discussed, what I already talked about?
Yes, Vitaly, I do have a few questions. First of all, thank you for the very clear presentation. It looks great. But I was curious, can you say what properties typing guarantees a program? So like, for example, in system F, effectively a well-typed program terminates. In Java, the types guarantee that you basically get memory safety. So you don't have the wrong memory shapes going into the wrong functions, and so on. So what properties do the meta types guarantee for meta programs?
Okay, I would say that saying the Java types guarantee memory, say memory safety. I wouldn't say that actually, but maybe you are talking about
I'm using it in a very specific sense of memory safety. Yeah. So, So yes, we have to be. There are lots of edge cases in the case of Java. There are lots of edge cases in the case of Scala. In the theoretical world, like System F, we know that well-typed System F programs terminate. And then when we move over to the practical world, there are very constrained versions of properties that the type systems guarantee. In the case of meta, the question still stands. What properties does a well-typed meta program have over an untyped meta program?
Well, I would say well, I'm looking at it from the following angle, right? So if you have some like well-typed program and well-typed library, it guarantees that either you have correctly typed values as an input of the function, or you have bad type error. I wouldn't say, like, example, that it guarantees okay, maybe it's about program is executable, right? So, but it guarantees the correctness of the program in terms of type matching if all values and all functions are well typed. But I'm not sure I I can explain. How to say, explain it or express it in some short way. Like we guarantee the program is correct, right? So you probably. I'm not sure if you can build the program with types, I mean in meta, which guarantees correctness of the program in all sense, but some subset of programs will be correct.
There's a probably a difference to make between the type system potential and the type checker, the built-in type checker inside the meta interpreter.
Yeah.
For instance, the backward chainer can do more than the built-in type checker. It's not going to prove that a program terminates out of the box, but you can make it do that.
Yeah, thanks. I'm just curious. That's all. I think it's useful to know why we type programs.
Yeah. Sorry, Greg, if I didn't answer your question, because I agree we could answer in this like in a deep theoretical sense. I mean, we could think about it in a deep theoretical sense. Basically, right now in meta, types are serving some like so for two purposes, right? So, to change the evaluation order, as I said, and to guarantee that if all values are typed, the function is not called with incorrect types, so somehow guarantees correctness of the function execution, evaluation.
Yeah, that's what I was going to ask Vitaly is what, it might be useful for the audience to understand what was the practical reason to introduce types, setting aside the abstract theory guarantees. Like in terms of practically implementing a language that you wanted to use, like what was the practical reason for introducing these basic types?
So should I? One of the reasons is like okay. So sorry, Ben. Probably I already like answered this, and I can repeat the answer. Maybe I didn't understand the question well. So I understand that like practical reason is that like maybe Alexey can put it in other words, which or add something to what I said.
Well, there were many historical reasons for us to introduce types, and actually Ben's interest in dependent types and homotopy type theory, or maybe model type theory was one of the non-practical but conceptual reasons, because we consider it such type systems as a way to represent knowledge and to perform some sort of reasoning, at least, over the types, the type definitions and functions as proofs of propositions encoded in type definitions And of course, practical reasons for introducing types is to reduce the number of errors produced by programmers. But basically, yeah, the current point, it's not precisely clear to what extent we need types or not. But if we say consider AI DSL, there is an opinion that using type systems for representing some knowledge or rules or whatever in AI DSL is a better way than using just custom symbols and custom expressions over them. So.
I would say that like having a type system, generally speaking, is just types they are allowing to define abstractions, and so just guarantee that the program is within the class defined by this abstraction, and that's it.
Yeah, I mean, if we go back historically into the early stage of meta design, I mean, we at one point we're looking at implementing meta in Idris, for example, which has a nice dependent type system, but a lot of Idris 2's efficiency, I mean, it comes from doing type checking of programs in compile time, and we knew that wasn't what we wanted for an AGI language, because we basically wanted the system to be able to introduce new types and invent new type checkers like in real time while running without having to stop and then recompile and relaunch the whole system. So it was clear that you wanted a basic foundation which had either no types or just a handful of very elementary types, and then if you're introducing a bunch of fancy types, be they dependent or homotopic or whatever, if you want to introduce a bunch of fancy types, these have to be done in such a way that the fancy types could be created in runtime. Then checkers for these fancy type systems can be created in runtime. So in that sense, for the more elaborate varieties of type systems, I mean, we want to be able to experiment with different ways of doing things, and have the AI system itself experiment with different ways of doing things. I mean, in an application context, one notion that we're interested to experiment with is if we want to apply meta in a particular domain, say bioinformatics, or say robotics, robot perception and movement, which are both things that are going on now. I mean, one way to structure that sort of application is to make type systems customized for those applications, and pretty much the difference between a type system customized for an application and just a set of predicates or functions that are customized for the application is having an efficient type checker for that application-specific type system. And this, I think, is going to be quite valuable, but we have to do some experimentation to validate that, right? And that ties in with the notion of creating domain-specific languages in meta, vaguely after the pattern used to create DSLs in Idris with domain-specific type systems that then inherit some of the type checking of the base language. So I mean, there's a lot of R&D to be done there, and I would say it's not yet clear precisely how it will come out in terms of how useful type systems will be versus other modes. But I definitely want to be able to play around with different specialized type systems in meta and see how it goes. I think, are we on to another session from Vitaly now? Is that right? But Vitaly, do you have another brief presentation explaining everything about how to implement meta?
Yeah, actually, we talked with Alexey about it, and I was not sure if I need to like to make a deep dive into the technical details of how NET implemented. So I actually was focused on another aspect, like explaining about explaining the standard library which is embedded into the Hyperon experimental implementation. Yeah, actually, yeah.
Yeah, but Vitaly, I missed a word that you said. You're going to focus on another aspect, which is something.
Yeah, I was going to talk about meta standard library. It is not that technical, how it's implemented.
The meta standard library sounds very useful for folks who are going to be playing with meta in practice. So yeah, going into that for a few minutes sounds valuable.
Yeah, one of the reasons is that Alexey in his examples, probably other people.
Alexey's examples use the standard library, right?
Yeah.
So we might as well see what the library is. So yeah, I guess we're going to deviate slightly from the written program. We will not have Vitaly tell us how the meta interpreter works. Instead, it's too hard to convey in half an hour, and he will instead run through some of the meta standard library functions, which will make Alexey's presentation on advanced uses of meta more comprehensible, since Alexey uses those library functions. And I think some of the talks in the afternoon using meta for probabilistic reasoning, reinforcement learning and such also use the standard library functions. And knowing what they are is of non-zero value. So yeah, back to the amazing Vitaly Bogdanov.
Okay. Probably about 20. Now, okay. I will explain some basic functions which I used almost in every meta program. And yeah, as I said, it can be useful to understand other people's example. So the first one we already have seen is match, which just queries the atom space with some pattern and returns the result. And match has actually two. There are two items about match which should be understood. So the first one is match can return no result. So if we are searching for something which is absent in the space, it just returns empty result. It doesn't handle the empty result itself. So it's inconvenient sometimes, and match can be used to match two atoms. For example, if you want to check if something is matchable, you cannot use match because match expects a space as a first argument. There is another function, let, to compare two atoms. Which returns exactly, which unifies two atoms and returns the result of if unification was successful, returns the set argument with variables filled by values, but actually it also cannot handle the empty result, so it just returns empty. And thus, recently we added the unify function into the interpreter, like relatively recently, which actually can do both things. It can query atom space and it can match two atoms, and it also can handle empty result, returning something when the result is empty. So you can also use it to match two atoms. Sorry. And you can use space as the first argument. So, okay, I will just add this fact into the space. Unfortunately, something doesn't work. Not sure what it is. Okay.
You
Do
can
you
use
need
and
space
space.
parameter?
No?
You should use cell.
No, sorry, maybe, yeah, so, sure, sorry. Okay, I added fact twice. By the way, yeah, if you add some atom twice, it is not duplicated and it stays in the space a couple of times. Okay, so unify is more universal than wet and match, and actually one technical detail why it can be used to query space, it is because space itself is grounded atom, which is, as I mentioned before, is a grounded collection which can be matched with other atoms, and match of the grounded collection with other atom effectively just queries this collection. Here, for the atom space, the query, the match logic is implemented as a querying of the space by the pattern, but also users can implement custom matching logic, thus implementing custom collections which has like different logic for matching with other atoms. For example, like I don't have implemented, but one can implement example dictionary. Let's say and matches with like here the dict is constructor of the dictionary, which takes a list of pairs key value, and matching logic finds the pair with required key and returns the value.
So it is built-in, right?
No, it is not built-in. I just told this example as a as example of the possibility. It is really simple to implement such dictionary, and it is implemented at one of the examples. I mean, in the Hyperon experimental repository, there is an example of dictionary implementation. I can try to find it if you want right now. But okay. So it's trivial to implement. This is like one of the possibility how you can change the matching logic. Okay, another two important functions which are also part of the standard library are collapse and superpose. Let's say we have some non-deterministic function. Okay.
I'm sorry, Vitaly, I just have a question. So once you have implemented dict, you can actually call match and replace the space by your dict construct, correct? And it's going to...
You cannot call match on dict actually because of type system. Type system expects, I mean, we could implement the matchable type and make spaces and dictionaries are instances of the matchable type. It's possible, but it is just not implemented right now like this. So mesh explicitly requires, I can probably show you, it explicitly requires space as the first argument.
Okay.
Yeah, so it explicitly requires space as the first argument, and it will not. But it's a good idea to implement matchable type and use it on like any atom which implements custom match logic. Actually, match and unify are not so different, so there is no reason to use match. Probably no reason to use match when you can use unify instead. Okay. So if you have some non-deterministic functions like color, which returns different colors, you may want to get the result of this function somehow handle it. So, for example, filter it or something. And to do this, you can use collapse function, which gets non-deterministic result of the function and represents it as an expression which contains all results. So there is a difference, right? There are just a collection of results, and this collection has one result, which is an expression with three results produced by color. You can also make a reverse operation like suppose which transforms expression into the non-deterministic result. So these two functions can be used to some extent to control the non-deterministic execution and somehow analyze the results in the middle of the evaluation, filter or modify them, and continue evaluation.
One question about, can you use Unify to look at color the way you can match? Like right now, we could sort of like look at the code for color using match. Can we use Unify to look at the code for color?
Yeah. Let's try it. Doing something like this. Okay.
Okay.
Yeah, also. Oh, okay.
Oh, that's good to see. Yeah.
Okay. So after returning the result, it tries to evaluate it, and it seems like the previous one. It seems that like it tries to call all the function definitions. Okay. One more, also more technical thing is a bind operation, bind function. When meta interpreter works on the program, first the program is parsed by parser, and the text of the program is converted into the atoms. And actually some atoms are converted into the grounded atoms, as I said. It depends on whether parser has special pattern for recognizing this. For example, when we type some number and it is feeded to parser, parser recognizes this number because it has a regular expression which recognizes the number, and specific atom constructor bound to this regular expression. When it finds a number in the stream of tokens of the program, it calls the atom constructor and replaces string by the grounded atom, which is constructed by this function. And also we can modify parser lookup table and add additional token into it. For example, we have function new space, but you cannot just add atom into new space. For example, will it work? I mean, it creates new instance of the space and adds atom into it. You just cannot query the space anymore. You cannot write something like this because each time you call my space, it is evaluated and new instance of the space is created. So, for example, just to, because they have equal pointer identifier, you can think it is the same space, but it is not correct. So nothing is in this space, but you can use bind to create a token which references new space created. So this creates token MySpace, which references some instance of the space created once, and each time you are, for example, you can add atom to the space, and you can get atoms from this space. So you can add facts into the space and query it. Okay, so bind is also quite complex function to understand, but it's very useful if you are writing some programs, for example, operating with some spaces created once, or other collections, anything else.
We will talk a little about edge reduct operation as another pattern for doing such sorts of things.
Sorry, Alexey. No, I was not planning to do this. So.
It's okay.
Okay, yeah. Last example I would like to show is also quite unusual thing. Usually people doesn't use it, but okay, you can write a custom, for example, Python module to define. I'm sorry, I don't have view here. Okay. Where am I? So you can write a custom Python module. For example, this module exports a couple of Python functions. It imports some definition from the Hyperon Python library and exports two functions. One, it just prints hello or something, and other adds two numbers. You can use register atoms annotation to define a function which registers with atoms inside meta parser when the module is imported from the meta program. So we are defining two operations: hello, which calls the hello function, and add, which calls add function. And we can import it from meta program and call the functions, call the Python functions from meta. It is a Python meta integration which is heavily used in most of our examples. Even like standard library is written using this technique. So I would like to demonstrate how it works. First I need import Python module by name, and now I can okay, I need to add some argument. So I didn't add types into the Python program. It is the reason why it is not like gracefully returned error, but instead returned Python exception. So it was a quick example just to simplify it. So it can also add different numbers. Actually, this I wanted to show it to demonstrate how easily Python code can be implemented. There are many different details. Python code can be integrated into the meta code. There are many different details on how you convert values from Python into the meta and vice versa. For example, here values are converted automatically, but you can manually do this. You can also, as I said, implement some custom collections with custom matching procedures. And this is all what I wanted to say about meta. And actually, I want to share the last link. It's a meta tutorial site. It contains a lot of information about meta. It's really good tutorials on this topic. You can even run some code in the sandbox just on the website. So I just wanted to advertise it because it's much more complete than my talk, which is very restricted. I tried to cover as much as possible about how to program in meta. But if you're interested in this topic, please go to metaland.dev and read some tutorials on this topic. Okay, thank you very much. I think I need to pass. Okay, so I believe it should be a coffee break right now. So if any questions on the last part of the talk, please ask them.
I can't hear you. Yeah, great talk.
Thank you for your attention.
No, I'm just, I'm wondering, are we following the schedule that was posted? Because I think I'm up next if that's
So
the case.
there's coffee, we'll just pop out for 5 minutes, everybody could pop out, take a really quick break, we'll pop back in for Alexey, we're of course a little bit behind. As usual, AGI.
Oh, okay. So I've got someone on the hook, and for them, it's like almost 10 o'clock at night. So do we have like, I don't want them to hang on until midnight or something, so do we have a sense of, when,
Greg,
we might?
let me chat with you about most, Greg, and we'll just let everybody here in the room go for a break, and we'll be back here in 5 minutes, 7 minutes, so 20 after.
20 after, okay, sounds good.
Hey, bye, started.
Alexey, we are almost all sitting down and ready to start. So Alexey will present next, looking at advanced meta-examples, building on Vitaly's presentation of the standard library, to my understanding. So Alexey, take her away, please. I wasn't unmuted, sorry. Alexey, we're ready for you. Well, essentially ready for you. Please get started with the advanced meta-examples, and we're looking forward to it.
Thanks. Unfortunately, we didn't hear Ben's introduction, so I have a risk to say something that wasn't it, but I'd like also to say a few words about the progress of meta development. We had alpha release in late April, and this was a sort of milestone for which we were preparing for quite a while, and now we one of our main aims for core meta development is scalability, which will be discussed in the next subsession. But I would like to say that there is a lot of things going on in the core meta development, and for example, we have recently switched to minimal meta. It was under development for quite a while, and there were different stages, like we were trying to pull together the initial Rust implementation of meta and minimal meta, which Vitaly was working on. Then minimal meta was available as a compilation option, and recently we have finally switched to implementation of minimal meta in Rust as the main version of meta, and that's why our numbering switched from something like 0.1.12 or something to 0.2.0, and I've just updated the meta version on the website, which Vitaly mentioned. So the latest novel version of meta should be working on this website. And I would also like to say that while the meta language is still relatively simple, there are indeed so many aspects and combinations of these aspects which are difficult to cover in our presentations, and it's quite difficult to choose what to cover. In particular, as Vitaly mentioned, there is a bunch of tutorials on metalang.dev. These are still quite basic tutorials for a number of reasons, but we hope they are quite useful. And well, I will try just hopefully it will work, because it was updated very, very recently. I want just to show one optional idiomatic way of working with states, some information instead of bindings, and what Vitaly said at the end, it has very deep implementation specifics, implementation details, how a tokenizer works and so on, and this is also covered in tutorials if someone is interested, but modifying the tokenizer is quite specific thing, so another possible way to put some containers to have them to work with them is to put some equalities into the space itself. I guess it should be something like this. Yeah, it works. So instead of modifying the tokenizer, we add an atom to a space, and this is quite a convenient way. So we actually added another function into oops. Yeah, sorry. Another function to the standard library, which is called atreduct, which evaluates the expression before adding it to the space. So a new space will be evaluated, and grounded atom will be created, and this expression will be added to self, and we will be able to execute my space function to retrieve this grounded atom and to manipulate with it. So it's just an example that there is indeed a lot of things which can be discussed and described in MET, and it's quite difficult to cover them all. And when we proceed to the topic of my presentation, which is called Advanced Meta Examples, then there is even more things which can be presented, and it was quite a dilemma what exactly to show, and I decided to focus on just one extension of Meta, which is called MetaMod, which combines Meta and LLMs, and while it doesn't provide some advanced reasoning examples at this point of time, but it combines a lot of basic things which Vitaly mentioned, and it will hopefully show the benefits of using Meta. So MetaMod is created as a Python extension of Meta, and it can be imported. It is stored in its own report, and hopefully we will populate our registry of extensions or modules or libraries in Meta, and we will be using an automatic deployment tool for them, but right now you can just install MetaMod using PIP, so it's also a Python library, and it's quite convenient that you can represent your meta modules as Python libraries and deploy them using a PyPI tool and just install them this way and have access to them. So MetaMotor provides a gate to a number of LLMs, and ChatGPT was the first one. It was under development for about a year. I believe on the previous workshop I showed some ideas, just ideas how it will be implemented, and then we started implementing it for the SingularityNET assistant. Unfortunately, we have not been spending too much time on it because there are different things, different other things going on. But still, it's usable, and if you have an access to an LLM, you can combine it with symbolic processing from Meta, and it looks like it is an ordinary Meta code with just a few grounded symbols, like ChatGPT agent, which can be called with, on some meta expressions. We pass messages to ChatGPT as well as other LLMs and get a response from them. So if we execute this one, I'm not sure if it is readable enough, or should I make it a little bit larger?
I can see it.
Okay, so we will get some a response from ChatGPT. We can add some additional messages, and we can make functional calls. For example, in this case, we have a pretty simple function which just returns I don't know. In the case when this function is called by, well, it is not called by ChatGPT per se, but ChatGPT returns some structure which can be interpreted as meta code. For example, if we instruct ChatGPT to always perform a function call and pass the function which is described like call this function to respond to every user question, and if the question is what is my name, the response will be I don't know, and we will call it. We will actually get I don't know, but if we don't pass a function to ChatGPT, then it will answer something by itself, like I don't have access to personal information. Or if we, for example, instead of answering just represent what the function receives, then it actually receives what is my name as its first argument, because ChatGPT returns the functional call with this argument. So as you can see, it's pretty simple basic integration of LLMs, calls to LLMs inside NET, and we can do different stuff with it. But this is only the beginning. We can do a lot of more interesting things. And this is just an example to show that if the function is non-total and it receives an argument which doesn't match with any quality defined for this function, we will see a not reduced version. So it's really the call to LLM results in returning some metacode which is fairly evaluated further in Net. So if this code can be evaluated, it is evaluated, otherwise it remains unreduced. So there is a lot of things which we can do with this combination of LLMs and meta. For example, instead of just having a hard-coded response like I don't know, we can perform actually some computations in meta. For example, here we have a function which simply returns the expression passed from the functional call from LLM for further interpretation. And we instruct LLM to convert the user query to an expression in a scheme or Lisp format. So once again, if we would like to see what is happening, ChatGPT will return something which can be in this case interpreted as a meta expression. But before proceeding to this example, I need to say that besides vanilla LLM agents, MetaMotor supports agents in Meta. So we can write some code which can be reused, and if this code contains a response function, it
Alexey, if you can pause just for a moment, our room disconnected. Let me get that here back up on the screen here.
You lost Wi-Fi?
Wi-Fi, I think.